Chapter 2 of differential calculus is limits and continuity. So notion of a limit, let f be a function that is defined on an open interval containing a but possibly not defined at a itself. So this statement defines the limit of the function f of x as x approaches a is equal to L, wherein L is the value that the function has as the point A is approach. So example 1, evaluate the limit of x plus 3 as x approaches 2. So using a tabular form for the solution, so we shall have x and y. So you just assign values for x approaching 2. So approaching 2. So let's say negative 2, negative 1, 0, 1.99, 1.999 as x approaches 2. Then solve for the values of x. Just substitute the values of x in this equation. So negative 2 plus 3 is equal to 1. So y is equal to 1. Negative 1 plus 3. So this is equal to 2. 0 plus 3, 3. 1.99 plus 3, 4.99. And 1.99, 9 plus 3 is equal to 4.999. Until x approaches 2, wherein 2 plus 3 is equal to 5. So this is only a simple evaluation of limit. So the limit of x plus 3 as x approaches 2 is equal to 5. Answer. Next example. So evaluate limit x squared minus 1 over x minus 1 as x approaches 1. So clearly this is not defined at x equals 1, so that is f of x does not exist. So nevertheless, the function does have a limit as x approaches 1. Thus, the limit of x squared minus 1 over x minus 1 as x approaches 1. So this does not exist, since if you substitute 1 in this equation, so we have 1 squared minus 1 over 1 minus 1, we shall have 0 over 0, which is an indeterminate function. So we can simplify the expression by factoring the numerator, hence the limit of x squared minus 1 over x minus 1 as x approaches 1 is equal to the limit of factoring out the numerator, x plus 1 times x minus 1 divided by x minus 1 as x approaches 1. So cancel out x minus 1 and x minus 1. We have now limit of x plus 1 as x approaches 1. So from this simplification, we can now substitute x approaches 1 in this equation. So substituting x is equal to 1. So the limit of x plus 1 as x approaches 1 will be equal to 2. Answer. Example number 3. So find the limit of x squared minus 16 as over x minus 4 as x approaches 4. So this equation is again an indeterminate, since f of x does not exist, because if you substitute x is equal to 4 in this equation, 4 squared minus 16 is equal to 0, and 4 minus 4 is equal to 0. which makes it an indeterminate function. So evaluating the limit, we can simplify the expression, then evaluate the limit. So solution, limit of x squared minus 16 divided by x minus 4 as x approaches 4. We can factor the numerator. So this is equal to limit of x plus 4 times x minus 4 divided by x minus 4 as x approaches 4. Cancel out x minus 4, cancel out x minus 4. So therefore, upon cancelling out x minus 4, we will have limit of x plus 4 as x approaches 4. So this is equal to 8. Answer. Question number 4, or example number 4. Evaluate the limit of square root of x squared minus 1 over square root of x minus 1 as x approaches 1. So evaluating the limit, we have the square root of 1 squared minus 1 divided by square root of 1 minus 1. So this is equal to 0 over 0, which is indeterminate. Now we express the quotient into single radical, then evaluate the limit. That is the limit of square root of x squared minus 1 over square root of x minus 1 as x approaches 1 is equal to the limit of square root of x squared minus 1 divided by x minus 1 as x approaches 1. Then from here we can factor the numerator side. So this is equal to the limit of x plus 1 x minus 1 divided by x minus 1. Then cancel out as x approaches 1. Then cancel out x minus 1, x minus 1. So this is equal to limit of square root of x plus 1 as x approaches 1. So substituting x approaches 1 in this equation, so we have square root of 1 plus 1. So this is equal to square root of 2. So the limit of square root of x squared minus 1 over square root of x minus 1 as x approaches 1 is equal to square root of 2. Answer.